All right, so what I'm going to do today is I'm going to talk about thermochemistry introduction. So first thing we need to know is in thermochemistry we focus on what a spontaneous process is. A spontaneous process is something that takes place naturally with no apparent stimulus. When we're talking about thermochemistry, we're talking about not having to add heat energy into it. Is basically what we're talking about. So a non-spontaneous process requires something that has to be added to it, thus heat or energy. So if you talk about, all right, so it would be like the example of a ball rolling down a hill is spontaneous. Ice, if you set a piece of ice out on your table at home, it will spontaneously melt. A non-spontaneous reaction would be like a ball rolling up a hill. The only way you could get the ball to roll up a hill is you'd have to add energy to it. Energy, the definition of energy is the ability to do work. There are all different kinds of energy that you've learned about in your different science classes. This chapter is going to focus on thermal energy or heat energy. That's really what we talk about. There are two different types of energy. There's potential energy, which is stored energy, which is the ability to do work, and kinetic energy is actually doing work. So potential energy is stored energy. Kinetic energy is the energy of movement. So if you look here, the water up in the waterfall here has potential energy. It slowly converts into kinetic energy as it falls. Another example would be this dude up here on a ladder on his roof. It's not safe, no one's holding it. Is potential energy because of his position off the ground. If the ladder gets kicked out and he falls, that is an example of kinetic energy. All right. What do we focus on in thermochemistry? We focus on the system. What is the system? The system represents some sort of chemical reaction, usually in a beaker. That is our system. Then what happens is we do, energy is either going to come or go, flow into a system or flow out. So energy coming out of a system has a negative sign because it's exothermic. So energy is being released out to the surroundings. And energy going into the system has a positive sign. We call that endothermic. So if energy is going in, it's positive. If it's going out, it's negative. Remember the SLG rule, solids, liquids, and gases. If you go from a solid to a liquid or from a liquid to a gas, in order to do that, you have to add energy. So the delta H value, or heat, is added. It's positive. If you go from a gas to a liquid or a liquid to a solid, we say the delta H value, heat is being released, so it would be exothermic, and the delta H value would be negative. Now, first law of thermodynamics we say is energy is neither created nor destroyed. So what's going to happen is it's just going to change form. So it's going to go from one form to another, constantly changing, neither created nor destroyed. One of the things you have to be able to calculate is your internal energy balance, or your internal energy value. That's like your account balance of your bank account, basically. It's how much energy you have in a system. So how do you figure that out? Well, what you do is you calculate your delta E by adding two numbers together. And all that matters is the sign of the numbers. You just have to get the signs correct. So if your E is a positive number, it means your system has gained energy, kind of like your account balance. If you put $200 in your bank account, it has a positive value associated with it overall. So you would have a positive sign. If you go to the ATM and remove $100, it has a negative value associated with it. So internal energy, or delta E, is just the amount of total account balance as far as the energy in a system. How do we figure it out? We use the first law of thermodynamics, which is just Q, which is heat, plus W, which is work. All you're doing is adding two numbers. You just have to get the signs correct. So if you look, heat. If you add heat to a system or you heat it up, we give it a positive sign. If you give off heat from a system or lose heat, cool, it gets a negative sign. If work is done on a system, it's associated with a positive sign. If work is done by a system, it's associated with a negative sign. So if you look, here's the first problem. They want you to calculate 100 grams of magnesium is heated. So it's heated from 100 to 50 to 100, a process that requires 870 joules. So I'm going to go Q plus W is going to be equal to my value for heat, right? Well, my Q value, if I'm heating it, it's going to be positive 870 joules. No work is done, plus 0, my overall account balance, or my amount of energy in this system, is going to go up by positive 870 joules. B, gas expands slowly while heating and does 200 joules of work. If you go back, if you do work, if work is done by the system, it is a negative sign. So I'm going to say negative 200 for my W, or work, plus it gains 350 joules of heat. So 350 joules of heat is gained. So when I add the two together, I get a overall adjustment, or account balance, goes up by 150, positive 150, bringing me a delta E of 150 joules. All right, here's another one, practice one. Calculate the change in the internal energy system. It absorbs 140 kilojoules of heat and does 85 joules of work. Well, the sign for absorbing is going to be positive 140 joules, plus, if it does work, it's going to be negative 85 joules. So when you do that, you calculate it out, you find out that your answer is going to be a positive 55, would be your delta E. State function. Thermochemistry, there are state functions in thermochemistry, so they're dependent on only the initial and final states of a system. What does that mean? It means that we don't care what your account balance, all you care about is your account balance. You don't care if you took out money out of the ATM, $100 5 times to get negative 500, or you took out 500 bucks at once. Either way, your overall account balance is going to be down by 500 bucks. So a state function means that regardless of whether or not how the changes happen, all you care about at the end is what the account balance is for energy. Any state function in chemistry has to do with, we just care about what the overall change is and nothing else, not how it gets there. All right, and exothermic means energy is released. Sign with an exothermic reaction is negative. Endothermic means that energy is absorbed by the system, so we give a positive sign. Heat going in, endothermic, positive delta H. Heat going out, exothermic, delta H, or enthalpy, which is heat, is going to be equal to a negative value. That's what exothermic means. One of the things you have to be able to do in chemistry is define a reaction coordinate. This is a reaction coordinate graph here. I make you draw it on your paper. You put energy on the right. You put reactants, and products are labeled with a little line. And in an exothermic reaction, the amount of potential energy listed here on the left, or the Y, the products always end up lower than the reactants. It is an exothermic reaction, so overall it loses energy. The account balance goes down. That's why exothermic reactions have a negative sign. Endothermic, potential energy is listed here. Boom, on the Y, you have the reactants and the products. At the end of it, the products have more energy. They have gained energy, or they've gone up. So the delta H is increased, or the delta potential energy is increased. So basically it is gained heat, or gained heat energy. So we say delta H is positive. Graphically, it looks like this. Boom. That's what a endothermic reaction looks like. Calorie. A calorie is the amount of energy required, heat energy, to raise the temperature of 1 gram of water from 15 to 16 degrees Celsius. That's a scientific calorie. A dietary calorie is actually a kilocalorie, 1,000 of those. That's what's on food packages. Key thing that you need to know for this is you need to know that a calorie is equal to 4.184 joules. So a calorie is equal to 4.184 joules. Now, one of the key things in this chapter that all the calculations stem from is something called the heat equation. You guys did this last year. It's very simple. It's MC delta T, MCAT, basically is what it comes down to. You have M, C, and delta T. You plug those numbers in, it gives you Q, which is heat, hence the heat equation. So you take three things, multiply them. This is adding, but you get the idea. You know what I meant by that. Anyway, so this is the total overall heat equation. If you look, mass has to be in grams. Whoa, mass has to be in grams. Final temperature minus initial, because it'll always tell you the problem from this to this. So it's final minus initial. And specific heat is a value. Every substance has a different specific heat. So it's MC. This is rearranged a little differently, but it's the same thing. Just move the C over here. MCAT. So it's basically MC delta T. Final minus initial times specific heat. This gives you heat in joules. A lot of times they'll want you to convert it to kilojoules. You do that by just dividing by 1,000. So here's an example of a problem. Amount of heat. So they're having you solve for Q. Q is going to be equal to MC delta T. Well, what do they tell you? 8.5 kilograms of water, can't have kilograms, so I change it to 8,500 grams. Right there. Specific heat of water. If you don't know, the specific heat of water is 4.184 joules, or 1 calorie. And then finally, temperature. They're raising from 2. The 2 is going to be the final, so I set up 84 minus 12.5, and then I just do the multiplication, and I get the answer. So the setup is M is mass in grams, C is specific heat for water, you're expected to know that, and delta T is the from 2. The 2 is always going to be the temperature final. This is going to be your temperature initial. Whoops, temperature initial. Okay, next one. If you look right here, they do it for different substances. 24.8 gram piece of copper, they want to know the heat in this case. They can have you solve for any of the variables in the equation. So if you look, you could solve for any of these variables. They would give you heat in a different equation. But this one, they want heat again. So I take 24.8 grams of copper goes there. Specific heat of copper in this case, if it's not water, they have to tell you what it is, or you solve for it. 0.385, and then finally temperature change. Heated from 22.5, so 22.5 will be my initial, to 178.6. Plug that in, and then do your calculations, and you find your Q, or your heat. The homework involves calculating out your Q value, or calculating out MC delta T. Do 5 of those, and then make sure you review the video and know the questions, because there might be a pop quiz on thermal chemistry to start the class period. In fact, there will be. All right, have a good evening. Later.